Hey guys, Mr. Smith here, and in this video lesson, our first of our 7th unit, um, we're going to one, see that exponential expressions or sometimes equations, sometimes functions can be displayed in different forms, and that we can use that idea to start solving exponential equations. And that's what this unit is all about. We're taking a deeper dive into exponential equations and logarithmic equations, developing tools for solving equations. Should be fun. So let's get started. I'm working in Cami today. Just found that to be. I'm just enjoying this tool a bit better as opposed to putting my stuff in a PowerPoint. So we'll see. I might, depending on the day, I might switch back and forth. Um, but I have in mind a little miniature investigation for you guys to do. You can, if you'd like to, sketch these two functions in Desmos if you want. Or you can sketch them by hand using some tools from your grade 11 course. And what I'd love for you guys to do is to sketch these two functions and investigate what happens when you sketch these two. You'll hopefully notice something pretty cool and to think about why this actually happens. So I'd like you to pause the video and give that a try, and unpause when you're ready. I'm going to now just like kind of walk through this idea. So to graph the first function, this is I'm going to graph the base function 2 to the power of x. Just by drawing some simple powers of 2. I can do much better than that, I think. That's somewhat better. This is the base function y equals 2 to the power of x. And we're going to be transforming that base function for the second one as well. And y equals 2 to the power of x. All right, let's look at the first one. 2 to the power of x plus 2. We know that adding 2 on the x gives a horizontal translation left 2 units. So if I take all those points and move them left 2 units, all those powers of 2 units, excuse me, all those powers of 2, just shifting them right. Get something like this. This is our function g for this guy. And a different transformation in part 2. 4 times 2 to the power of x, that would correspond to a vertical stretch by a factor of 4. So if we do that, taking 0.5, multiplying by 4 gives you 2. 1 by 4 gives you 4. 2 by 4 gives you 8. I guess you could do 0.25 times 4 gives you 1. What you actually see is that these two graphs are the same. These two completely different looking exponential functions actually produce the same graph. They're equivalent. So what do we notice? The two graphs are the same. Well, why did this happen? Well, we can talk about why this happened. Let's take, it really doesn't matter what our starting point is. Let's take the right-hand one for, continue to work in purple here. 4 times 2 to the power of x. So I can write 4 using a base of 2, right? 4 is just 2 squared. And we know when we're multiplying two powers to the same base, we can add the exponents. This gives us 2 plus x, which is the same as 2 to the power of x plus 2. Algebraically, those two expressions are equivalent to each other. We just showed that. So it's no wonder they produce the same graph. They're actually just two different ways to express the same function. Let's illustrate this idea just one more time, and then I think you guys will get the idea. So here we're doing a transformation of the base function 2 to the power of x. Draw that guy one more time. Again, hopefully you've tried this one on your own. If you haven't yet, I'd pause the video, just try to give these two functions a quick sketch. That's y equals 2 to the power of x. Over here, I'll just make this one right in green. 4 to the power of x is just your basic exponential function, y is 0, 1, and the y values are quadrupling every time. So 1, 4, we would get 2, 16, we get negative 1, negative 1, 0.25. Really, that's all we can sketch. Do my best there. Okay, that's the function there. All right, now what transformation is happening with the first one? We're done the second one. So for the, oh, you know what? That's actually really bad for the second one because it goes through 216. So there's actually no way it could look like that. Definitely needs to be fixed up. So it would shoot off more like this. Okay, I'm more comfortable with that. Okay, 2 times 2 to the power of, or 2 to the power of 2x. So the effect of multiplying the x by 2 is a horizontal compression by a factor of 1 over 2. So the 0.38 will get compressed to 1.58, 2.4 goes to 1.4, 0.12 goes to 0.52, the y-intercept is invariant, and then this point gets squashed halfway. Negative 2, 0.25 goes to negative 1, 0.25. And what you see is we actually get more points, but it's the same function as the function in part 2. What did we notice? Again, the two graphs are the same. And why this happen? Well, we can do some similar algebraic manipulation to show that these are equal. And this one, I might take the left-hand one, 2 to the power of 2x. We can use our power of a power rule for exponents, but in reverse, right? You can write that as 2 squared to the power of x, because the power of a power rule is that you multiply the exponents. 2 times x is 2x. It all checks out. And of course, 2 squared is just 4. So 2 to the power of 2x and 4 to the power of x are equivalent expressions. And this is the big idea, the purpose behind these little miniature investigations, is to say that the same exponential expression / equation can have multiple different forms, It can be expressed in many different ways. And this can be a useful tool for us to solving some exponential equations. So we'll see that in a moment. Again, exponential functions can be represented in many different ways. And what we're going to do right now is just an exercise in converting from one base to another. Here we did that in the last one. We wrote if you think of 4 in terms of a base of 2, we can show these two graphs are equivalent. So let's take these expressions, kind of building in complexity, and let's express these in terms of a power with a base of 2. So lots of space here. A really doesn't require any work. Hopefully you kind of know your powers of 2, right? 8 is just 2 cubed. Eight is the third power of 2, let's say. In a similar way, you might be able to reason out b, because 4 cubed is 64, and you might be able to figure that out as a power of 2. Alternatively, we can take 4 cubed, and we can write 4 as a power of 2 first. That's 2 squared. And then you can use your exponent rules, power of power, to the power of 6. So we use the fact that 4 is the second power of 2. And then we just use our exponent rules. 2 times 3 is 6. C is not so obvious. hopefully you recognize 16 and 32 are powers of 2. Um, and there's several ways to go about this kind of problem. I'll show you guys one way of thinking about it. Um, in this case, I'll just rewrite this out. Root 16 times the fifth root of 32 cubed. So using the stuff we've learned in our grade 11 course, we actually know that the root of 16 can be written as a power. That's 16 to the power of 1 half. The fifth root of 32 cubed can also be written as a power. That's 32 to the power of 3 over 5. Over 5 because it's fifth root, and then the 3 on top because we are raising that to the power of 3. Now this is kind of similar to let's say write its powers. It's similar to part B. We can write 16 as 2 to the power of 4. We can write 32 as 2 to the power of 5. And then we can use our exponent rules to simplify. 4 times a half is 2, and 5 times 3/5 is 3. 2 squared times 2 to the power of 3, 2 to the power of 5. So just using skills from earlier grades, A, B, and C, you guys could have done those, just building in complexity a little bit. But how do we write 12 as a power of 2? Without just guess and check. You know what I mean? So let's have a look at that. Let's do part D up here. I guess I could have managed my space a bit better. That's okay. So part D, we can't just write 12 as a power of 2. It's not like a nice power of 2, right? So in this case, we're going to set this up this way. What we're really looking to do is we're trying to find some k such that 2 to the power of k equals 12. Now, luckily, after our last unit, we actually have a tool to get us what the value of k is. And we're going to do that. We're going to get k by taking the log of each side. Common logarithm base 10 is fine. And recall, we have this power law for logarithms, where the log of this power is equivalent to k times the log of 2. And now we can solve for k. K is equal to log 12 divided by log 2. And we've got it. I'm going to just continue down here so we can kind of finish off the problem. 12 is equal to 2 to the power of log base 12 over log 2. Now, there's one more way we can write this, or 12 equals 2. If you recall, we had that change of base formula. Log 12 over log 2 is equal to the log base 2 of 12. This makes perfect sense if you dwell on it for a second. What does log base 2 of 12 mean? It means the exponent, so that when you raise 2 to that exponent, it gives you 12. Well, if you then do 2 to that exponent that gives you 12, obviously you're going to get 12, right? So this statement makes a lot of sense. And so you can always write any positive number as a power of any other positive number by using this strategy here. And log 12 over log 2 is perfect. Log base 2 of 12 is also good. But this actually illustrates a very interesting property. And it's this. So if you have some base to the power of log base A, your base is A, log base A of B, this is equal to B. And that can be, it's a kind of a really useful property that you might make use of. I know I make use of it when I teach the calculus course here and then. And the reason this works is that the exponent, the power a to the power of x and log base a of x are inverses of each other. So you guys know, more or less, if you do let's say you do the sine of 30, and then you do the inverse sign of that, well, you're just going to get 30 again, right? Because it's like the inverse of an inverse. They kind of undo each other. It's the same. It kind of works the same with square roots. If I do 4 squared and then I square root that, well, that's just going to give me 4, right? So it's kind of the same idea. So just tuck that little rule in your back pocket. Could be useful in times to come. But yeah, we can write any positive number as a power of any other one. So that's the big takeaway from this first example. We can write we can rewrite we can rewrite expressions in terms of different bases. Our first 3 there was pretty straightforward, but D, you can take any number and write it as a power of any other number using this rule. All right, so after exploring that, the only other thing we want to get into today is to get into, dip our toes in the water, just solve some these aren't going to be too overly complex exponential equations. So basically, equations that involve exponential expressions. And the strategy that we're going to use today is the algebraic strategy is we're going to apply a change of base. So how does that work? So let's look at our first example, part A. So in part A, hopefully what everybody recognizes looking at an equation like part A is that the two bases, 4 and 64, are kind of related. 64 is a power of 4. So our strategy for these guys is going to be to rewrite each side in terms of a common base. Here we'll do that by taking 64, and we know that 64 is actually 4 cubed. And so what we're doing here is I'm just going to write rewrite as a common base. That works well here because 4 and 64, again, 64 is a power of 4. And now we can go about solving this one. If we just take our time, we can apply the exponent rules on the right. We get 4 to the power of 3x. And here's the beautiful thing about this method. On the left-hand side, we have 4 to the power of x plus 5. On the right, we have 4 to the power of 3x. If those two expressions are equal and the base is the same, 4, that means the exponents have to be equal as well. So x plus 5 has to equal 3x. So what we're doing here is we're just equating the exponents. We can only do this though, exponent starts with an E. We can only do this when the base is the same. So that's why we had to change that base of 64. And now this is not too bad of an equation to solve. You can bring the x over. 3x minus x is 2x. And you get that x is equal to 2 over 5. Put a box around it. All done. I'm going to squeeze b in over here. And we'll do b in a similar way. So we have 4 to the power of 2x equals 8 to the power of x minus 3. So the idea with a is 64 could be written as a power of 4. In a question like b, 8 cannot be expressed as a power of 4 easily. However, 4 and 8 can both be expressed by a common base. That's the key with this question. So you do have to recognize that 4 can be written as a power of 2, 2 squared, and also 8 can be written as a power of 2, 2 to the power of 3. Now we can use the same strategy as A. We can clean up the exponents and we can equate the exponents. So on the left, we have a power of a power. 2 times 2x is 4x. On the right-hand side, we have another power of a power. We'll multiply the exponents. 3 times x minus 3 is 3x minus 9. And now we can equate the exponents. 4x equals 3x minus 9. Bring the 3 over, the 3x over. 4x minus 3x is x. And we get that x is equal to, in this case, negative 9. Put a box around that. So that's the idea. This is our first strategy for solving an exponential equation. Sometimes, like here, the base can be written in terms of a common base, and you can equate exponents. So we did that, maybe just to save some writing here. We did that here. And in the second question, we did that here. Part A only required us to rewrite one of them. Part B, we had to rewrite both in terms of a power of 2. And then once we did that, we could equate the exponents to get an equation that we can solve using skills from earlier grades. Now, one other method for solving these equations, as usual, you could use technology. Don't get me wrong; I want you guys to be able to solve things algebraically. But you can always check, and especially like maybe if the equations have like nasty numbers and stuff like that. Like sometimes if all you care about is the final answer, can be useful to use a graphing program like Desmos. So let's solve. It doesn't really matter which one we do. The first one will have a solution that it'll show up easier. So let's graph the two functions in part A. 4 to the power of x plus 5. X plus 5. And the second guy was 64 to the power of x. It just kind of does show it. So it looks like I can just move up here. There we go. And there we go. Just had to click on the function there. You can see where they meet. Did I type those in right? 4x plus 5. Oh, I didn't. I was like, why am I not getting the same thing? It's because it needs to be an exponent plus 5. There we go. So you can see where they meet. I did it again. What's going on? No. Desmos, x plus, maybe if I use brackets, x plus 5. There we go. So clearly the solution's not on not on what's visible there, but if we just keep going up and up and up, did I type that in right now? 64 to the power of x. Yep, and we got 2 to the power of 5. Yep. 64 to the power of 2 over 5. I feel like I'm having to go way too high for this. 64 to the power of 2/5. It's only 5. So it definitely did something. 4 to the power of x plus 5 equals 64 to the power of x. Oh. I was expecting my answer to be visible because you guys probably noticed this way earlier than I did. 5 divided by 2 is 5 over 2. 2.5. Okay, we fixed that up. All right, Desmos. 64 to the power of 2.5, 5 over 2, is 3,768. So I'm going to definitely need to change my window settings here. So let's go from, I don't know, -5 to 5, and maybe I'll start at like -2,000, and we'll have to go up to, I'll go up to about 40,000. Okay, there we go. And now we can see 2.5, 5 over 2, everything's okay. So yeah, if you can check these answers by graphing, but to keep in mind, like in this one, because we're dealing with exponential expressions, the point of intersection, you might have to change the scale significantly to see it. And here we did that. Of course, actually solving the equation correctly the first time would help, but we got it. All right. And that's it for this lesson, guys. A little brief introduction into one technique for solving exponential equations. We saw initially that we can rewrite functions, expressions by changing the base and getting equivalent expressions. And then we use this technique to solve some simple equations. Got some suggested practice for you guys there as usual. Again, please reach out if you need anything. Hope you guys enjoyed that lesson. I enjoyed giving it. Stay well, guys. We'll see you soon. Take care.